podcast is brought to you by LMU Munich.
Thanks a lot for the word, Matthias. And I'm deeply grateful for the organizers for giving me this outstanding opportunity to present our work. What I will tell you in my talk is about superstring scattering amplitudes and, most importantly, hidden simplicity therein. I will give some manifestations of hidden simplicity, which you can find in these three papers here. In these papers here, the first two together with my former PhD supervisor Stefan Stieberger and Carlos Mafra, and the second one with Carlos Mafra. Both of them are sitting in the audience. My talk essentially has three parts. As an appetizer, I will start with hidden simplicity at tree level. I will show you that tree-level amplitudes involving any number of open string states can be decomposed into the kinematic factors of the underlying field theory. So in the end, Super Young-Mills field theory already knows quite a lot about the first order of string perturbation theory. Then let's come to the main dish. In the second part of my talk, I will show you some relationship between tree level and one loop of open string perturbation theory. I will argue that some ingredients from the tree level amplitudes will be recycled to form the kinematic factors, all the polarization dependence of the one loop amplitude. And finally, as a dessert, I will say a few words about our methods at work. We have been using the pure spinor formalism, and I'll try to sketch a few main ideas why this one is so powerful to attack multi-particle amplitudes. All right then, let's start with the appetizer section. John Joseph was so kind to already advertise the upper half of this slide. Here on this slide, you find the complete tree-level amplitude involving any number n of open superstring states. So here on the left-hand side, you have a color-ordered amplitude among open string states. So they are associated with a particular cyclic ordering of the gauge group generators on the color side. So this stringy tree amplitude to all orders of alpha prime, it decomposes into kinematic factors of the underlying Young-Mills field theory. So here, these guys in green are objects from Super Young-Mills field theory, which certainly exist independently on strings. And if you take a closer look, we are summing over n-3 factorial terms. Here, these permutations pi only act on a subset of legs, namely 2, 3, 4, up to n-2. And it's essential to note that these field theory objects carry all the polarization dependence of the amplitude. The remaining ingredients, these stringy functions f pi, only depend on momenta, not on polarizations. So let me tell you what these f pi's are. For each permutation of the Young-Mills amplitudes, you get one generalized Euler integral that carries alpha prime dependence. Yeah, it arises from the n-3-fold Worldsheet integrals that you have to perform here at tree level. A few more comments on this slide. The formula you see here is consistent with the field theory limit. As you send alpha prime to 0, all the massive string modes become infinitely massive and decouple. So the left-hand side should better reduce to the color order Young-Mills amplitude. And indeed, the right-hand side, which has a sum at the beginning, well, this collapses to just one single term because most of these f pi functions fade away as alpha prime goes to 0. Here in this Kronecker delta notation, you see that only one function, where the permutation pi is the canonical one, survives as alpha prime goes to 0. Concerning the scope of this formula, first of all, we have been deriving this in the context of 10-dimensional n=1 Super Young-Mills with 16 supercharges. And you're always free to dimensionally reduce that. So the formula is certainly valid for all states of n=4 Super Young-Mills in 4 dimensions. In that case, you can plug your favorite spinor helicity representation of A Young-Mills right here. So then you can apply 4-dimensional spinor helicity methods if you like. Then, after breaking of SUSY, the formula will certainly remain valid for gluons only, because gluon tree amplitudes in string theory do not depend on what happens to the internal dimensions and what happens to the supersymmetry. So it's always valid for gluons, and if you like to preserve some SUSY, it's valid for the full gluon multiplet. Next, I invite you to take a closer look at these functions f pi, and they will depend on dimensionless quantities formed by alpha prime and the bilinear in momenta. I'll be using dimensionless Mandelstam variables throughout my talk, so please memorize this convention here. And these Sij, they show up in our functions in the way as displayed. And I should draw your attention to the part on the right-hand side thereof. Here, this is the interesting part, which comes from the OPE contractions between the vertex operators. And if you completely simplify this amplitude to get A. Young-Mills field theory subamplitudes, then there's a very peculiar basis of 1 over C the polynomials. You always get a combination of a Mandelstam variable, SPQ, divided by the corresponding difference of vertex operator positions. And this rigid pattern, which we find here, SPQ over CPQ, has two very nice consequences. First of all these functions are local. There are no kinematic poles because the Mandelstam numerator here cancels every potential kinematic pole that could arise from the integration. And as a second nice property, it makes sure that these functions here are maximally integration by parts friendly. What I mean by that, if you use the fact that a total derivative integrates to 0, then you find relations between several packages of this type, SPQ over CPQ. This is very interesting when you want to manipulate those functions and reduce them to minimal basis. And yeah, precisely this is the topic of my next slides. What are the basis dimensions involved? First of all, on the kinematic side, we are recycling the field theory data, different A. Young-Mills permutations. And as John Joseph told you, there's a basis involving n-3 factorial elements only, which generate all the A. Young-Mills permutations by linear combinations thereof. To do such a basis decomposition, you have to go by two steps. First of all, there are Kleist-Coif relations, which bring you down to an n-3 factorial basis. Here is an example. Please note that there are constant coefficients plus minus 1. As a next step, you also need BCJ relations involving Mandelstam coefficients, and this is the last step of the reduction process. Like John Joseph said, they can be derived from string theory. Okay, let's come back to the complete tree-level amplitude for the string states. It's made of two sectors. We've just been looking at the former sector involving A. Young-Mills. They fall into an n-3 factorial basis. And now the question I want to ask is, do we have a harmony between these two sectors? Does the second sector of string functions fall into the same basis dimension? And the answer is yes. There are dual systems of equations that govern the A. Young-Mills on the one hand side and the functions f pi on the other side. So first of all, we have Kleist-Coif to reduce A. Young-Mills to n-2 factorial. And the dual identities among the integrals are partial fraction, some very trivial algebraic identity on the level of the integrand. And now let's finish the reduction. Let's go to n-3 factorial. This is BCJ on the A. Young-Mills side. And the dual identity for the functions is integration by parts. Clearly, this comes from a total derivative that integrates to 0. And here you recognize a relation with Mandelstam coefficients because of these Sij in the numerator. Yeah, here you see a perfect harmony between the field theory ingredients sitting in the tree amplitude of string theory and, on the other hand, hypergeometric functions which take care of all the stringy corrections of all the alpha prime dependents. Let me now move on to the main dish, the one-loop amplitude. We have computed the n-gluon amplitude at one loop in string perturbation theory for any multiplicity n. And the result is very analogous to tree level. Also, these one-loop amplitudes of n-gluons, they decompose into alpha prime independent kinematic factors. And this time, the essential kinematic package is not the A. Young-Mills tree amplitude, but instead, this is the very first string correction which we have just looked at in the open string tree amplitude. So here, these AF4 are defined by being the alpha prime square coefficient of an open string tree level amplitude. And each of these permutations of AF4 are accompanied by a particular worldsheet integral. Here, these integrals over some functions which I call GI, they carry all the alpha prime dependence of the one-loop amplitude, whereas the polarization dependence is entirely sitting in these packages AF4. And due to the tree-level result, all of these AF4 can in principle be reduced to A. Young-Mills. So you see that A. Young-Mills field theory at tree level knows everything about the kinematics for string theory at tree level in one loop, to all orders in alpha prime, because whatever these functions here do, these power series in alpha prime are associated with kinematic factors that ultimately boil down to field theory. The combinatorical pattern is slightly different than at tree level. This time, my sum does not go over n-3 factorial terms, but instead, the combinatorics is governed by so-called unsigned Stirling numbers of first kind. I'll say a few more words about them later on. Now, the validity of this formula is a bit more restricted than at tree level. Clearly, once you go to loops, the spectrum clearly matters. So please don't trust this result in theories with less than 16 supercharges. Let us now zoom into the kinematic factors. We have these AF4, which are defined as the alpha prime square contribution of the open string tree amplitude. So by doing expansion of these functions, you can identify the AF4 packages as A Young-Mills permutations together with quadratic polynomials in the Sij. Remember, there's one power of alpha prime for each Sij. So you see, starting from multiplicity 5, the definition of AF4 mixes different super Young-Mills orderings. So here, for instance, you have a different color ordering from what you want to compute on the left-hand side. And we have closed formula for these alpha prime square corrections. So in principle, I have no problems to give you the analogs for any multiplicity n. This is one topic in some work in progress. And I should add, this is a follow-up project to a recent work with Stefan Stieberger and myself about motific multi-zeta values encoding the alpha prime expansion. Unfortunately, I won't have time to present this work as well. Okay, how do these AF4 show up in the pure spinor computation of one loop amplitudes? Well, I have to admit, these AF4 don't show up directly. These AF4 are objects with a cyclic symmetry, but in the first place, the computation gives us different objects with slightly different symmetry properties. I want to introduce you to some BRST invariant kinematic factors. These are the result of maximally simplifying the integrals. And each of these C's are BRST closed, and they are all linear combinations of the AF4. But the symmetry properties which these C's satisfy are a bit different. I have to say that leg number 1 is always discriminated in the rest of my talk. Leg number 1 is inserted through an unintegrated vertex operator, whereas all the other legs come from an integrated vertex operator, and the other legs have to be inserted into 3 slots. So my kinematic ingredients have 3 slots, labeled by A, B, and C, and they are symmetric under exchange of any 2 slots. And more remarkably, in each individual slot, they behave like tree amplitudes in the sense that they have a reflection symmetry and a Kleist-Coif relation. So for instance, here you see if a slot has 3 labels, it essentially behaves like a 4-point A Young-Mills tree amplitude. However, there are no BCJ relations. Now, once I know about these Kleist-Coif relations, this implies that each of these slots essentially behaves like a cycle. And now I want to count the number of independent BRST invariants, which I get in my string computation. And this combinatorial problem is the definition of the Stirling number. It's the way how you can distribute k elements to 3 different cycles. And the number of k elements are all my external states, except for number 1, which is special. So clearly the basis dimension is S1 minus 1, n minus 1, 3. But I should come back to the story of the AF4. I tried to advertise that these loop amplitudes can be boiled down to A Young-Mills tree. Now, how can I reduce the C's to an AF4 or to an A Young-Mills? Well, the answer is all the AF4s, these string corrections, they can be easily expanded in terms of C's. And the rule is quite simple. You write down all the C's with the same sequence of external legs like on the left-hand side. And now you put the commas separating the slots in each way possible. So this is a formula which can be easily given for all multiplicities. And because of this formula, each of these C's, which you get in the string computation, they are implicitly given in terms of AF4. And as you see, there are no Mandelstam invariants involved in this decomposition. So these relations must be quite simple. And moreover, since the C's fall into a Stirling basis, the same must be true for the AF4. Or even more than that, there must be several Kleist-Coif-like identities between different AF4 permutations, such that the number of independent ones are given by the Stirling number. And here's one example for such a Kleist-Coif-like identity. Here, the sum over 6 different permutations of 5-point AF4, this is strictly 0, and we call it Kleist-Coif-like because there are no Mandelstam coefficients. Now, the same kind of relation has already been observed in a completely different context, namely in QCD, for finite one-loop amplitudes where all the external helicities are set to plus. So in this 2011 reference, these authors observed a couple of Kleist-Coif-like relations for QCD amplitudes. And we can reproduce all of their relations for our objects AF4. And a partial explanation for this has been out already since 2006, where Stefan and Tom Taylor observed that in the MHV helicity configuration, these AF4 are proportional to the finite QCD loop amplitudes with all plus. So we are having some sort of the non-MHV completion thereof. Now that we have discussed the kinematic factors in one loop amplitudes, let me say a few words about the worldsheet functions along with that. So here is the expression for the integrated one loop amplitude. And the very first line should not be a surprise at all. Of course, there are n-1 worldsheet integrations to perform. Of course, there's a modular integral over all conformally inequivalent cylinders. And of course, there's the universal Koba-Nielsen factor from the plane waves. But now, the interesting stuff is waiting in the second line. There you find everything which is due to the OPE contractions among the vertex operators. So here this is the non-trivial part of my statement. You can always decompose the full one loop amplitude into a basis of BRST invariants C, which are given by AF4 in the end. And each of these C's multiplies a different worldsheet function, which I'm calling G in this slide. The basic ingredients for these worldsheet functions, this is the cylinder Green's function. So think of this object as the one loop upgrade of the 1 over C polynomials that we had at tree level. And just like in the tree amplitude, they are accompanied by an associated Mandelstam variable. Here you have this Sij over Cij combination. And once again, this leads to local behavior, at least for the planar case. And it is maximally integration by parts friendly. Now, please remember this convention that Xij is essentially the Mandelstam variable times the 1 over C upgrade at one loop. And now, let me give you the explicit expression of the worldsheet function, which is associated with a C. It turns out that the worldsheet function G factorizes on the 3 different slots of the C, of the BRST invariant. So let me draw your attention to the very first factor here. This guy here is the dual worldsheet function to the first slot of labels along with the BRST invariant. And of course, the sum is running over all possibilities to put n-1 legs to these 3 slots here. Here are some examples for what I've just said. It starts getting interesting at 5 points where there's the first OPE contraction, and at 6 points you encounter 2 different topologies of BRST invariants. Since you can do 2 different slot splittings, the first line of the 6-point amplitude has 2 plus 2 plus 1 as a slot splitting. That's why the X dependence factorizes. And in the second line, you have a 3-particle slot with 2, 3, 4, which gives rise to a more convoluted X dependence. Now that I've told you quite a lot about this one loop amplitude in open superstring theory, I want to point out a duality of this object. A duality to something from tree level, which is also made of AF4. By definition, the color-dressed tree amplitude at order alpha prime square is precisely given by the cyclic sum over AF4 permutations together with a trace over gauge group generators. And since I have this C decomposition of every AF4, then clearly also the color-dressed tree amplitude can be decomposed into the Cs. And the symmetries of these C bases, they have a very important implication to the color structures involved. Namely, these gauge group generator traces are projected to a small subset of color tensors. This subset always involves a symmetrized 4 trace. Here I'm defining this D1234 tensor as a symmetrized 4 trace. And it turns out that the only surviving color structures here are of the type D times F to the n-4. So you have 1 symmetrized 4 trace and structure constants otherwise. Okay, so both these objects, the one loop amplitude and the color-dressed tree-level amplitude at order alpha prime square, both of them decompose into the C basis of kinematic factors. And the former is multiplied by some worldsheet functions, which I've given to you. And the second one is multiplied by some color tensors T. And to give you the explicit representation of these T's, I think it's more instructive to work with diagrams. So here you see the diagram, which is associated to a particular color tensor. And I'm representing the symmetrized 4 trace as a box. And I have chosen my basis such that leg number 1 is always dotted into the box directly. And all the remaining n-1 legs, they form some kind of tree-level subdiagram which is placed at the remaining 3 corners of the box. And in this diagrammatic notation, a cubic vertex represents a structure constant. And I should emphasize, each of these tree-level subdiagrams in the corners of the box, each of them correspond to a particular factor of the worldsheet function associated with that. So this subdiagram, the circle, is dual to this function here of the x variables. Here is the full-fledged expression in terms of color tensors, but I think the diagrams are nicer. So let's go to the example section. Again, diagrammatic notation. At 4 points, these color structures are rather boring. There's simply one symmetrized 4 trace where all the external particles are sitting, and accordingly the G function is boring. And starting from 5 points, the OPE contractions translate into a diagram like this, and the color tensor along with that is a structure constant corresponding to this fork sitting at the upper left corner on the box. And accordingly, the 2 different topologies which you can have at 6 points corresponds to a more complicated contraction pattern of structure constants plotted into the symmetrized 4 trace. Please note the 2 different topologies here. Now, you might ask why I try to sell this as a duality. The reason why I'm talking about a duality is that the algebraic structure of the color tensors and the worldsheet functions are the same. Both of them fall into dual bases of dimension Stirling number. And in order to convince you of that, I have chosen 2 examples. The first one is the standard Jacobi identity between contracted structure constants. So here this is the standard Jacobi identity, which you might have seen billions of time at tree level of field theory already. And the dual statement on the level of the worldsheet function, well, in this case, this is a triviality. Because if you take this function corresponding to the color tensor on the right-hand side, then it trivially cycles to 0. But then the second example is certainly more interesting. For these color tensors with a symmetrized 4 trace, there's some kind of generalized Jacobi identity. So here, this is a 4-term identity where a cyclic sum equals 0. And now the dual identity of that on the side of the worldsheet functions, well, this guy here is an integration by parts statement. You can recognize this as a total derivative with respect to C2, which integrates to 0. Now, these are some manifestations of a duality between color and worldsheet functions. And once we have arrived at this point, I want to go one step beyond and try to extend the duality to a triality, which involves kinematics as well. You have seen in John Joseph's nice talk that very often color and kinematics are singing exactly the same tune. And since we have already shown that color and Zij functions obey the same system of equations, it's tempting to ask whether we can find numerators that also obey these symmetry patterns and the same identities. So the question I want to ask here, can we find representations for the 5-point numerators for these diagrams such that this sum here gives 0, dual to the color statement and the worldsheet function statement? Unfortunately, at this point, the answer is no, at least not so far. The pure spinor computation suggests a particular representation for these numerators, and so far they don't satisfy these dual Jacobis. However, we are now working on one-loop gravity amplitudes, and they give a hint of how these corrections might look like. So I hope to have some results on this in the near future. Now, this ends my main dish about the one-loop amplitude. And as a dessert, I want to say something about the pure spinor methods which have been involved in these computations. The pure spinor formalism is a manifestly supersymmetric approach to the superstring, and amplitude computations in the pure spinor framework are supersymmetric in all intermediate steps of the computation. And one particular advantage of the pure spinor formalism, which we have been using, is you can compactly represent a 10-dimensional Young-Mills amplitude. And the pure spinor formalism suggests a particular set of superfields in order to do so. Here, these superfields M on the right-hand side, you can think of these as some tree-level sub-amplitudes with one leg off-shell. And there's a very nice representation for each color-ordered Young-Mills tree amplitude in terms of a few of these M superfields. And in order to arrive there, you do not need to do any explicit computation. Instead, the answer is fixed by first principles, namely by the pole structure, which you want to have in the tree amplitude, and secondly, by BRST invariants. It's under very good control how these sub-amplitudes m behave under the action of the BRST operator. So these first principles led to the simple answer for A. Young-Mills. And now for the stringy tree-level computation, the task was to identify these sets of superfields within the CFT correlator. And this turned out to be possible. Now a similar story applies to the one-loop amplitudes. The kinematic ingredients are these AF4s, or the equivalent basis of C objects. And for both of them, we have another representation in terms of pure spinor superfields. This time, these BRST invariants are made of quartic expressions in these tree-level sub-amplitudes. And the first step of the computation was to figure out what are the BRST invariants that I can form from these building blocks. And then we could do the explicit CFT computation at one loop, and then it was no more difficult to identify these ingredients C within the CFT correlator. And John Joseph made one comment that these pure spinor superspace methods are useful to derive manifestly dual kinematic numerators. To understand this, one has to go to this representation here of the A. Young-Mills amplitude. So on the right-hand side, you find many, many diagrams. And if you combine these diagrams with the associated worldsheet integrals in the string computation, then the field theory limit of these worldsheet functions tell you how to combine these objects on the right-hand side to form these dual kinematic numerators. And the basis of diagrams is n-2 factorial dimensional in this tree-level case. So this is why the construction works. Let me now conclude to what I've told you. First of all, we have been looking at the superstring disk amplitude, and I told you that it decomposes into a kinematic sector, which is borrowed from field theory. So all the polarization dependence in the open string tree amplitude is carried by the super Young-Mills field theory. And then there's an infinite tower of alpha prime corrections sitting in these functions f pi, and it turns out that they fall in a dual basis of the same dimension n-3 factorial. So there's perfect harmony between kinematic data from field theory and from stringy physics sitting in these f pi on the other side. Moving on to one loop, I've shown you a similar decomposition for open string one loop amplitudes. The kinematic dependence decouples from the alpha prime physics. This time the kinematics is carried by the alpha prime square correction to the tree level amplitude. But according to the result above, this is nothing new compared to super Young-Mills field theory. So once again, it's the kinematic package from super Young-Mills field theory which also governs the one loop amplitudes of the open superstring. And this is true to all orders in alpha prime. Now that we have shown this up to one loop, it's really tempting to believe that also the higher orders of stringy perturbation theory will do the same. So we believe that this hidden simplicity, field theory knows everything about polarization dependence in string theory, we believe that this pattern holds on for the complete stringy perturbation series, at least in these scenarios with 16 supercharges. And another extra bonus which we find at tree level in one loop is that the combinatorial structures are dual to many other objects from unrelated areas. For instance, these worldsheet functions in one loop turn out to be dual to some color tensors which you have seen at tree level for the first time, namely at order alpha prime square. To derive these results, it was crucial for us to have the pure spinor formulation at hand, because it helped a lot to streamline the computation and to identify the kinematic packages therein. Now there are a couple of follow-up projects that are suggested by these results. First of all, it would be nice to further investigate the duality which we have found in one loop. Cij functions are similar to color tensors, and hopefully they are also duals to some kinematic factors which are participating in a gravity amplitude at one loop or even higher loop orders. And we hope that this duality complex might also give inspiration for field theory, how to efficiently organize amplitudes in supergravity and super Young-Mills, each of which in the maximally supersymmetric configuration. Now, it was funny to see that some alpha prime corrections from tree level give rise to the basic packages of one loop in string perturbation theory. And it's tempting to believe that the higher alpha prime corrections at tree level, that they will be the essential input for higher loop amplitudes of the string perturbation theory. That's why we want to find compact pure spinor representations for higher alpha prime corrections for tree amplitudes. And if we have arrived at this point, it will be easy to answer the question, are these the building blocks for higher loop, yes or no? And by the way, the pure spinor setup for computing 2-loop and 3-loop amplitudes is close to being understood. Okay, this is all what I wanted to say. Thank you very much for your attention.
Amazing, right on time. Perfect. Questions, please?
Hi. In your one-loop calculation, what was the topology of the string worldsheet?
We have been agnostic to the worldsheet topology. You can adjust the integration domain such that it either reproduces a planar or a non-planar amplitude. Oh, well, it's running out of energy. But this slide is really good. Yeah, I didn't tell you what the integration range is for the C's. All that I've been using is that a total derivative with respect to a Z integrates to 0. Otherwise, this full reasoning should be valid equally for planar and for non-planar amplitudes. The difference will be sitting in the behavior of these integrals.
Are you restricting to SO32?
Sorry?
Is your analysis restricted to SO32?
Oh, and also we did make no reference to the gauge group since we are considering color stripped amplitudes. But I should admit, yeah, we are blind to the anomaly part of these amplitudes. It's understood from which sector of the computation the anomaly comes from, and we have been analyzing the non-anomalous part of this open string tree amplitude.
Because there'll be problems with tadpoles also.
Tadpoles? Let me rephrase it. BRST invariance was used as a guiding principle, not really used, but at least it guided us to identify the packages. And then there's another sector which is far outside these BRST invariants, and this one will carry the anomaly part.
Mm-hmm.
So do you have any insight into whether such a relation would carry over to higher?
Oh, sorry, I had some acoustic problems.
So very interesting relation between one loop amplitude.
Here we have a backup.
So very interesting relation between various part of the amplitude. So is there do you have any insight of whether or how this can carry over to higher genus, higher loop amplitude?
Mm-hmm. We have a lot of evidence that the alpha prime cube correction to the tree amplitude is very much present at 2-loop level. So there is a partial representation in terms of pure spinor building blocks, and these do indeed show up in the pure spinor computation of 2-loop. But at the moment there are still some residual objects in the cohomology of the BRST operator which we could not yet match with the alpha prime cube correction to the tree amplitude. So it looks like there's a little bit more involved, but it could be, for instance, an AF4 from alpha prime square together with some decoration by a linear polynomial and Mandelstam's.